regarding the previous class. Any question or any doubt? Okay, so if not, then okay, so there are some corrections which I would like to make. Okay, so here in the algebra, okay, so there is some sign difference which I will mention now. So Ji, so this is not correct. So there is a sign difference just. Okay. So I have Jij. So let me erase this right hand side. Okay. So Jij is I epsilon I j k jk. Okay. Previously we were writing I epsilon I j k lower jk. That is minus of I epsilon I j k j upper k. But that was the mistake. So there is a plus sign here with k up. Okay. And then ki ji kj is I epsilon I j k kk, and ki kj is minus I epsilon I j k jk. Okay, fine. Okay, so now we have seen the we are discussing the generators for Lorentz transformation, and we express these generators as we express the Lorentz transformation as exponential of the generator. Okay, and the generator satisfy the given algebra. Okay, so you can so this is the form of the Lorentz transformation, and you can go back and see what happens for particular. If I consider the particular Lorentz transformation, then how one can write this matrix, this lambda omega. Okay. Yeah. So yeah, maybe this part I will redo a bit. Okay. So this part, I think I need to do some algebra. Okay. So now we want to write this expression, okay, in slightly different form. Okay. So I define ji, okay, as half epsilon ijk j jk. Okay, remember this is one index object. So out of I have this j mu nu. Okay, so there are 6 independent matrices called j mu nu. Okay, out of these I will use the special parts like jk's. Okay, and I will combine that with epsilon ijk, and I will form a 3 vector, ith component of some 3 vector. Okay, so this is j1, j2, j3. Okay, so j1 will be epsilon 1, 2, 3, j23 plus epsilon 1, 3, 2, j32, and so on. So here the j and k is summed over. Okay, fine. So this is one thing. Okay, and then remember there are 6 parameters also. So there are 6 parameters omega mu nu. Okay, so what I will do, I will define again a 3 vector theta k, okay, by half, okay, epsilon I j k, okay, omega ij. Okay, so this is theta k. Okay, so with these definitions, with these definitions, one can write omega mu nu j mu nu in slightly better form. Okay, omega mu nu. Okay, so let us express. Okay, so let us first evaluate omega ij in terms of theta. Okay, so if I consider, so theta k is half epsilon I j k omega I j. Okay, so if I multiply from the left epsilon L m k theta k, this would give me half epsilon L m k epsilon I j k omega I j. And remember, there is a summation over I j. Okay, and now there is a summation over k. Okay, but you can use the product of two formula for product of two epsilon, and you can show easily that this object is nothing but minus omega ij is summed over k is summed over, so it is minus omega ln. Okay, so you can invert this relation basically and write omega in terms of thetas. Okay, so omega lm is equal to minus epsilon L m k theta k. Okay, or this I can also I can write as epsilon L m k. So I am taking these 3 up, so there will be relatively minus sign, so it will become plus and theta k. Okay, there, fine. So now in terms of, now you can use this omega lm, okay, here. And I have also, maybe in the last lecture, I also defined another object called yeah, ji0 as ki. Okay, so ji as half epsilon ijk jk and ji0 as ki. Okay, if I define this and omega I0 as eta I. Okay, so these two relations together with this, okay, I can use to simplify omega mu nu j mu nu. Okay, so I can write omega mu nu j mu nu as half, sorry, minus omega ij epsilon I j k j k. Okay, so here I substituted the form for j mu nu. Okay, and this I kept as it is. Okay, so you have to do a little bit algebra. Okay, maybe if you want I can do that, but it's not necessary. You can also easily do. But, yeah, correct. Okay, so omega mu nu j mu nu is nothing but this, and ji0 is nothing but uh, ki. Okay, so you use these relations, these two are important relations. Okay, so you use that and express this, okay, in this form, okay, which is nothing but this. Okay, fine. So Lorentz transformation can be written in this form also. This form is equivalent to our previous form, this one. This one, there is no difference. Okay, written in just slightly better language. Okay, sometimes this form is useful, sometimes this form is useful. Okay, clear till this? Any question till this point? Any question till this point? So let us apply to some particular case. Okay, so let me apply this for a particular case. So suppose I want to discuss a particular Lorentz transformation which is a rotation, and that also rotation about say z axis, that is axis number 3. Okay. So let us see what we get. Okay, so rotation about third axis, that is z axis. Okay, so in that case I have to define what is Lorentz transformation. Okay. So let me do that. So delta x mu, can write it in a better language. I just wanted to see just a minute. Yeah. So delta x mu is equal to omega omega rho sigma j rho sigma. Okay, and the rho sigma j rho sigma, there is a minus I by 2 here. Okay. It's mu nu entry and then x nu. So this is our delta x nu. Okay, and let us see what this gives us for rotation. So I want to obtain the lambda matrix, lambda omega for rotation. Okay, so that is our job. Okay, so for rotation, can you tell me what are these omega rho sigmas? Okay. What happens to this omega? Anyway, diagonal entries will be 0 because this is antisymmetric. So what will be omega 0 I for rotation? For rotation, what will be the parameter? Omega 0 I.
0.
0. Okay, because this omega 0 I basically represents boosts. So this will be 0. Okay. What will be omega 1 2? Okay. What will be omega 1 3? What will be omega 2 3? If I know this, then I know basically omega 2 1, omega 3 1, omega 3 2. What will be omega 1 2? What should I take? What should I take for omega 1 2? Can anyone tell me? Okay, first let us use this. Let us see what we will get. Okay, if I use that here, then as you can see, this relation I can write in the following form: minus I by 2. Okay, in the rho sigmas are summed over. Okay, so I will get the contribution only from spatial indices. Okay, if rho equal to 0, sigma equal to 0, then anyway I am going to get 0. If rho equal to 0, sigma equal to I, then also it is 0. Okay, so I will get on the contribution only from omega ij, that is spatial indices, jij. Okay, omega mu nu x nu. Agree? Okay, I use this relation, this equation. Okay, because we are discussing rotation. Now I have rotation, but that is also about z axis. Okay, so there will be some further simplification in these parameters. Some parameter will go to 0. Okay, now which parameter will go to 0? Can anyone tell me? First of all,
Omega 1 3, omega 2 3.
Pardon? Which parameter go to 0?
Omega 1 3, omega 2 3.
Correct. Okay. So omega 1 3, omega 2 3, because these will represent the rotation. This will represent the rotation about y-axis, and this will represent rotation about x-axis. But I'm not rotating along those axes. So I have some non-zero parameter here, omega 1 2. But omega 1 2, okay, omega 1 2, we have the form. Omega 1 2 is minus epsilon 1 2, then it has to be 3, okay, theta 3. Okay, so I will substitute here. So omega 1 2 is minus epsilon 1 2 3 theta 3. Okay, and epsilon 1 2 3, epsilon 1 2 3 is minus 1. Okay, so let me, yeah, epsilon 1 2 3 is minus 1, epsilon upper 1 2 3 is plus 1, epsilon upper 1 2 3 is plus 1, so epsilon lower 1 2 3 will be minus 1. Okay, so this will be theta 3. Okay, so the interpretation of this is, it is just an angle through which we are rotating about z axis. So omega 1 2 is theta 3. Okay, and this is 0 and this is 0. So I can use it here. Okay, so if I use that, what I'm going to get is the following: minus I by 2. Okay, omega ij. So I will get omega 1 2 j 1 2. If it is omega 1 2 here, then I have to take j 1 2 only here. Okay, mu nu x nu. Okay, clear? Plus there will be another term, omega 2 1 j 2 1. Agree? Okay. But I will use the antisymmetry of omega and j, and I will add. So there will be factor of 2 here. Okay. So I will get minus I omega 1 2 j 1 2, and now there will be these indices mu nu x nu. Okay. So this is equal to minus I omega 1 2, omega 1 2, we agreed that it is theta 3. Okay, and j12 will be equal to, okay, so j12, so we have to invert it. Okay, so there is a similar to this, one can invert this relation. Okay, so let me write that. So j12, yeah. Yes, it will be, just a minute, I will see what is that relation, so that we should. Give me a minute. Yeah. I can invert this relation, and I can write j ij as minus epsilon ij k, okay, jk. Okay, so I will use now form for j12. Okay, j12. Okay. So j12 is same as j12, because I have to down these indices twice, so there is no relative sign, j12. So that is equal to minus epsilon 1 2 3 j3. Okay, minus epsilon 1 2 3 is minus 1, so it will be j3. Okay, so it is j3 here. And mu nu x nu. Okay, so delta x mu is basically this. Okay, so this gives us how coordinate transform, what is the change in the coordinates under the rotation about z axis. Now you consider mu equal to 0. If you consider mu equal to 0, so you have to put 0 here. Okay, and nu, so nu can take value 0 or I. Okay, but for both things, so recall what is J3. Okay, J3. So you can, so there are two ways to determine. Either you determine the matrix J3, or you can use our earlier, somewhere I have given the rotation matrix. Okay, and I asked you to calculate. Yeah, this one. Okay, form like this. Okay, so you have to use form like this, or you can use the form matrix form for J3, okay, which again requires this form. Okay, form, see, this is J23. Similarly, there will be J12 and there will be J13. Okay, so I have the matrix for J12. From that, I know the matrix for J3. Okay, in that matrix, okay, 0 I will be zeros just. Okay, and 0 0 is also 0. Okay, so I will get vanishing contribution from this. Okay, so if I put mu equal to 0, then so let us do that. So delta x0, it will be minus I, minus I. See. So I will get minus I theta 3, okay, J3, it's 0 0 x0, so 0 0 component, minus I theta 3 J3 0 I xi. Okay, in both the cases, in both the terms, I will get, so J3 0 0 element is 0, so I will get 0 here, and J3 0 I is also 0. But for that, you should know what is the matrix for J3, and that you can calculate if you know J12, J13, etc. So in particular for J3, you should know J12. Okay, and that I gave as an exercise. Hmm? So the form of matrix J3 will be such that 0 0 entry will be 0 and 0 I will be 0 again. Okay, so I will get 0. Okay, so that is expected because under rotation is x0 is not going to change. Okay, similarly, suppose if I put delta x3, okay, that means mu equal to 3. What I'm going to get? Minus I theta 3 J3. Okay, it's 3 0 x0 plus, so there is a minus I theta 3 J3, okay, and 3 I xi. Okay, so this is again 0. Okay, this will be I can take now, since it is there is 3, I can take only 1 and 2. Okay, so this is also 0. So the form of J3 will be such that this is also 0. Okay. Same thing happens for, so delta x3 is 0, delta x0 is 0. So basically there is no change in the z component that is expected because we are rotating about z component, and there is no change in x0. Okay. And remaining things, delta x1 and delta x2, they will transform according to what we expect from rotation. Okay, so rotation about z axis. So delta x1 will be, so you can substitute. So delta x1 will be minus theta x2. Okay, this you can show. Okay. And delta x2 will be plus theta x1. Okay. Hmm? So this is infinitesimal rotation about z-axis. Okay, fine. So as expected, we have no change in time component, no change in z component, and I have infinitesimal changes in x and y components. Okay, so this is just a one example. Okay? And now you know what are these transformations. Okay, you can just construct this finite Lorentz transformation. Okay, so in this case, our finite Lorentz transformation will be lambda omega equal to, now omega, all the omegas are 0 except omega 1 2, right? And that is equal to theta 3. Okay, this is equal to e to the power minus I to the power minus I. Okay, theta, so in theta here will be replaced by theta 3 j3. That's it. Okay, yeah, so this will be the finite Lorentz transformation. Hmm? Okay, great. Same thing you can do for boosts. So you take now the boosts, okay, and construct. So this is important. Okay, so for the boost you have to choose. Suppose you are taking the boost along x-axis. So you choose the parameters like that. Okay, and get the form of lambda omega. Hmm? Okay, so we'll get the expected results now. So what we have? We have the Lorentz transformation, okay, which is written in the exponential form. Okay, so any proper orthogonal Lorentz transformation can be written in this form. Okay, and J and K are the generators for the boost, for the rotation, and boost respectively. Okay, so here your J and K are the generators for rotation and boost. So there are 3 generators for rotation and 3 for boosts. In all, we have 6. Hmm? Okay, and we also know what is the algebra. Okay, we also know the algebra among J and K. Algebra means the commutation relations among J and K. J, J, K, K, and JK. Okay, good. Okay, now we'll do a transformation, a linear transformation on these J's and K's. Okay, and let us see what we will do. So we'll do a linear transformation on J's and K's. But to note that, okay, but to do that, we should note that here this J generator for rotation, okay, is Hermitian. Okay. However, the generator for boost is anti-Hermitian. Okay. How I can say that? Because you know the form for J mu, right? Okay, J mu nu is what? Okay, J mu nu. Great. Yeah, you can either use this one or you can use this form where I have written, yeah, this form. Okay, J mu nu rho sigma, you can write in this form, and from that we obtain these matrices. Okay, J01. Okay, basically you can see from here. Okay, J01 is what? J01 is minus K1. Okay, because J10 is K1, so J01 is minus K1. What is J01 dagger? It is equal to dagger of this, so it will be I replacement and minus sign. Okay, so there will be minus of J01. So this is basically J01 will be minus of minus K1. Okay, clear? Therefore, K1 dagger is equal to minus K1. Okay. So the boost generators, okay, are anti-Hermitian. You can see from this, you can find other matrices J02, J03, and you just explicitly take the dagger. Okay, so you'll get the minus sign. So K1 dagger is minus K1, K2 dagger is minus K2, K3 dagger is minus K3. However, the rotation generators, for example, here, okay, because of this structure, you see here 0 minus I 0. Okay, you concentrate on this part. Because of this structure, you will get no sign change. So J12 is Hermitian. So you have Hermitian rotation generators, but anti-Hermitian boost generators. Okay. Yeah. So let me construct a linear combination of J's and K's. Okay. That linear combination is given by M equal to J plus IK by 2. Okay. And N equal to J minus IK by 2. Okay. Note that because of this I, this M is Hermitian now. M dagger is M, and also this is also Hermitian. N is also Hermitian. Okay, so I have now two Hermitian generators. Okay, M and N, okay, which are defined, which are related to your J and K in this fashion. Okay, fine. And now I will use these redefined generators in the commutation relation. Okay. So let us evaluate the commutation relation between M and N. M, N. Okay. So basically, I would like to evaluate, say, M ith generator, ith M type generator, and its commutation with Jth N type generator. Okay. Fine. So what will be this? This will be equal to 1/4 commutation relation between Ji Jj plus Ki Kj, okay, minus I times Ji Kj, okay, plus I times Ki Jj. Okay, so if you, and you know what are these commutation relations. Okay, so if you substitute that, you will get 0. You can use this commutation relation if you want. I can do, but it's trivial exercise. You just substitute this known commutation relation between j's and k's. Okay, ji jj we know, ki kj we know, and ji kj we also we know. Okay, so if you substitute that, you will get 0. So m I n j is 0 for all I and for all j. Therefore m n commutation is 0. Okay, so this tells us that I have two types of generators which commutes among themselves. So it is the first sign that we might get decoupling. But this is not enough. Okay, let us evaluate. So this is first one. Let us evaluate commutation relation between M and M. Okay, that means I need to evaluate Mi, Mj. Okay, what will be this? Mi, Mj is equal to. So again, you can I can write this, but you can evaluate by using the known commutation relation. So it will be ji jj plus I time ji kj plus I time ki jj, okay, minus ki kj. Okay, and if you substitute the commutation relations for this, you will get minus I epsilon I j k mk. So that is nothing but I times epsilon I j k mk. So important thing is that M commutation relation gives you M, not N. Okay, that is important. So the algebra is closed, the M type algebra is closed among itself. Okay, so M commutation relation gives you M only. And similarly, N commutation relation, so Ni Nj equal to minus I, you can show that Ni Nj is equal to minus I epsilon I j k nk. So this is also equal to I epsilon I j k nk. So N commutation relation also gives you N. So I have two types of generators, okay, which commute among themselves, and among themselves they reproduce the rotation algebra. But instead of one rotation algebra, I have two rotation algebras. So M commutation relation gives you one rotation algebra. And N commutation relation gives you another rotation algebra. Okay. Recall what happens for rotation. For rotation, you have Li, Lj commutation relation. This is your usual angular momentum. Li, Lj is equal to I times epsilon I j k Lk. This is what is happening now. Okay. So M type commutation, commutation relation gives you same kind of algebra. NN commutation relation gives you same kind of algebra. MN commutation relation gives you 0. Okay. This means that the algebra of Lorentz generators for Lorentz transformation of Lorentz transformation, okay, can be split, okay, into two parts. Okay, both parts gives you algebra which is same as rotation algebra. This is what I am calling as rotation algebra. Okay, or it has a name. It is called SO3 algebra. Okay. So SO3 is a group. So it is the algebra of SO3 group. Okay. So you can think these LIs are the generators of rotation, pure rotation. So the entire Lorentz algebra is nothing but the direct product of two rotation algebras. Okay, so I have SO rotation algebra for SO3. So that usually in group 3 language it's written in small letters SO3. Okay, direct product with SO3. So this small s denotes algebra, not the group itself. So the algebra of generators of Lorentz transformation is nothing but SO3 direct product with SO3. Okay. The important point is MM and NN commutation relation gives you M and N. Hence, the MM commutation relation closed among themselves. So there is another word, closedness of algebra. Okay. So MM commutation relation closed among themselves. NN commutation relation closed among themselves. And there is a decoupling because MN is 0. So this redefinition, okay, this redefinition of generators, okay, allow us to identify the Lorentz algebra as a direct product of two rotation algebras. Is this clear? Okay. Although I am writing this as SO3 cross SO3, the correct way of writing is SU2 cross SU2. SU2. Where S, so SO3, so let me mention S, there is some terminology. SO3 is group of 3 cross 3 orthogonal, and that means real matrices. Okay. That is SO3 with determinant equal to +1. Okay, so S stands for spatial. Spatial means determinant equal to +1. Okay. O stands for orthogonal, and 3 stands for 3 cross 3. Okay. So I have spatial orthogonal group of 3 cross 3 matrices. Okay. Spatial orthogonal group in 3 dimensions. It is a group of 3 cross 3 orthogonal matrices with determinant equal to +1. Okay. This is the group of rotation. Okay. So rotation matrices falls under this category. Okay. Basically, rotation set of all rotation matrices forms a group. If you exclude the parity, if you exclude the space inversion, okay, because for space inversion this will be -1, so that is not S here. So I cannot put S there. On the other hand, SU2 is the group of 2 cross 2 unitary matrices. Okay, unitary means the entries are allowed to be complex. Entries of these 2 cross 2 matrices are allowed to be complex. So this is the group of 3 cross 3 orthogonal matrices with determinant 1. This is the group of 2 cross 2 unitary matrices with determinant equal to plus 1 again. Okay. One can show that this SU2 group, there is a relationship between SU2 group and SO3 group. This group is a group of complex matrices, but with unitary condition. This group is the group of real matrices with orthogonality condition. But there is a relation, one can think this as also the group of rotation in some sense. In fact, it is actually the correct way of understanding the rotation. Okay. There is a relationship between SU2 and SO3. Okay. Okay. Why I'm discussing this? Why I'm telling you this? Because you know, in the case of spin, okay, you have these polyspin matrices. Okay, those matrices are not unitary matrices. Okay, they are complex matrices. Okay, they are traceless Hermitian matrices. Okay, clear? One can use those matrices, exponentiate them appropriately with parameter. Okay, and that will generate the rotation in the space of your two components. Okay, clear? That transformation is same as the rotation. One can derive, maybe I will spend some time over this because this is important relation. If you understand this, then everything will be easy. There is a relationship between SU2 and SO3. And I will spend some time over this. Okay. But till this point, any question till this point that the statement that the Lorentz generators, okay, can be written as direct product of SO3 cross SO3. Any question?
So, sir, while in order to see how the wave function transforms under Lorentz transformation, we will need to construct an operator. So that operator will be based on J and K.
Yes, correct. Okay, so any Lorentz transformation can be written in terms of J and K. So J and K, basically J's and K's generates the Lorentz group. Like your angular momentum generates the rotation, right? Similarly, your boost and rotations generates the Lorentz group. If you know J's and K's, you know what is lambda omega. You have to just fix the parameter. You have to just tell me what Lorentz transformation you are considering. I can give you its matrix elements. Its matrix, that 4 cross 4 matrix. Okay. It's not essential, but it is useful. Okay. One can obviously go back to our earlier classes, right? One can write that most general Lorentz transformation matrix. The usefulness of this will become clear. Will be clear later on. Okay. Any other question?
So, sir, where will we use this M and N matrices? If the operators are based on J and K, then
see why. Okay, so the question is where I will use this M and N. Okay, the point is that M and N are not defined arbitrarily. Okay, they define through this relation. Okay, so if I know J and K, I know M and N. But why I did this? Because I can see that the Lorentz generator, the algebra of Lorentz generators now can be seen as made up of two SO3 algebras. And now when I discuss the represent, see what I want to do, I want to act this Lorentz transformation lambda omega, okay, on the wave functions. Okay, but I cannot act lambda omega directly on the wave functions because these are whatever we obtain this lambda omega, this is allowed to act on coordinates, right? X mu's. And when lambda omega acts on this x mu, okay, I will get x prime mu, which is basically another inertial frame or Lorentz frame. Okay, so this is, we are still in the coordinate representation. Hmm? But that is not sufficient, okay, because ultimately I want how wave function, ultimately what I want how Dirac-Spinor transform or Dirac four component object transform under Lorentz transformation. For that I should know the action of lambda omega on that psi, right? This is four component object. Okay, I should know what how this lambda omega should act on this column vector. This is not your ordinary x mu. This is not your usual some v0, v1, v2, v3. This is not like that. Okay. Here, when I write this v0, v1, v2, v3, it is a four vector, and I know how the four vector transform under Lorentz transformation. Okay, that is what we are doing. Okay, if I want to check the transformation property of any four vector, okay, I can act lambda omega on that four vector. Okay. Given a Lorentz transformation, I construct this 4 cross 4 matrix. I will act that 4 cross 4 matrix on this 4 cross 1 column vector. I will get another, that is the transformed contravariant vector. Okay, or transformed column vector. Okay. I cannot do these kind of things here. I mentioned that this is not your, although I have written in column vector form, this is not your 4 vector. I don't know what is this because there is, see, there is no index right here. I have not written any index on psi like this. But still I have these four components. Hmm. So first of all, you have to clear this. I cannot act Lorentz transformation directly on the wave functions, or in this case, Dirac wave function or Dirac spinor. I'm avoiding calling this object as spinor because I have not mentioned anything about the spinor. In fact, we will define the spinor as certain objects which will transform in a certain way under Lorentz transformation. So till now, I don't know how this object transform. In order to do that, I have to construct appropriate representation of this Lorentz transformation. Okay. Clear? That is what we are going to do. Have I answered your question?
Yes, sir.
Okay. Now your question was why we require M and N. The M and N, once we write the generators in this form, okay, there is a way to classify the representations. In M and N way of writing, there is a clear way of representing these matrices or classifying these Lorentz transformations further. We will do that. It will become clear why I'm writing in M and N. Ultimately, I will write in J and K form only. Your Lorentz transformations are written in this form only, J and K. M and N allows you to identify appropriate representations. I will tell you what does that mean. Okay. But let us first spend some time on rotation. Okay. What happens in rotation? Okay. Any rotation in, when I say rotation, it's in 3 dimensions. Your usual Cartesian space, your real space. Okay. Any rotation can be specified by specifying a direction n cap and an angle, say phi. Okay. Yeah. The corresponding rotation matrix for chosen n cap and for chosen phi will have some 3 cross 3 representation. We'll have some 3 cross 3 form, 3 cross 3 matrix form. This, when it acts on coordinates, when Rn cap phi, when it acts on, say, vector x, okay, you will get another vector, say x prime, such that x square equal to x prime square. So the rotation keeps the length of the vector unchanged. This is nothing but this is another way of saying that the rotation matrices are orthogonal. R n cap transpose R n cap phi equal to identity. Okay. Here. Now, any rotation, because this rotation is a continuous, the parameter involved in the rotation is a continuous parameter. Any rotation can be written as the exponential of minus I, n cap is the axis, phi is the angle, dot j, where j's are the generators. Okay. And this j satisfy the following commutation relation that I already mentioned anyway. Okay, clear? This way of representing the rotation, okay, that is nothing but you specify an axis, that is n cap, and you specify an angle phi. Okay, so I will rotate about this axis by an angle phi. So n cap together with this phi defines the rotation. Okay, but this is a one way of defining the rotation. Another way of defining the rotation is through what is known as, you must have heard in classical mechanics, Euler angles. Okay. So you specify Euler angles alpha, beta, and gamma. Okay, there are 3 Euler angles, and you can write any rotation matrix. You can write any rotation matrix in the following. Okay. R alpha, beta, gamma is equal to R3, that is rotation about z axis by an angle alpha. Okay. Then rotation about y axis by an angle beta, and again there are rotation about z axis, old z axis, by an angle gamma. This is the Euler angle representation of rotation. Okay. Not representation, Euler angle parameterization for rotation. So there are 2 parameterizations. One is axis angle, so this is called axis angle and is called Euler angle. So both gives you a way to parameterize rotations. One is axis angle and one is Euler angle. Okay, I think there is some. Hello, can you hear me? There was some problem with the internet. So can you hear me now?
Yes.
Yes, sir.
Okay, so I don't know when the internet went off. So can you just tell me what was the last point you heard?
Euler axis angles and Euler angles.
Axis angle or Euler angle. So this you heard, right?
Yes, sir.
Yes. Yes.
Oh, fine. So one is axis angle parameterization and one is Euler angle parameterization. Okay, both are useful. And one can write these also in terms of generators. Okay, so in the Euler angle parameterization, okay, your R alpha beta gamma can be written as e to the power minus I alpha J3, e to the power minus I beta J2, e to the power minus I gamma J3. But don't try to write this as e to the power, so you cannot combine them because these are the matrices. Okay, you cannot just exponentially e to the power minus I alpha J3 plus beta J2 plus gamma J3. That you cannot write. You have to write it separately because, okay, you know this Baker-Hausdorff identity. Because of that, you cannot just simply write as exponential of sum of this. That you cannot do. So either you write rotation matrices in Euler angle form, which is this one, or you can write the rotation matrices in this form. Both are useful. Here J3, J2 means the rotation generator about z-axis and rotation generator about uh, y-axis. Okay. These allow us to know how any three vector transform. Okay, if I know this matrix, then I know basically how the transformations of three vectors. You give me any vector and I will act this 3 cross 3 matrix and I will give you another vector, which is basically the transformed vector under rotation. Okay. Now, what is representation? Okay. Representation in group theory is nothing but a map, okay, a map from group elements. Okay, say suppose G is a group element, okay, of some group, say capital G. Okay, it is a map from some group to a group of linear operators. Okay, so you consider a group G, okay, and let us consider any element small g in that group G. Okay, then the representation is what? You give me a G and I will give you a linear operator. Say, let me write that as RG. So this RG is a linear operator. This is linear operator. Your group element is not in general a linear operator. Okay, but the representation is a map from group element G to a linear operator. So basically, what I am doing, I will consider this map. I will act on all these group elements. Okay, elements of G, capital G, and I will get corresponding linear operators. Set of all linear operators also form a group. Okay, so this map is basically a map from any given group to group of linear operators. If these linear operators are real, then it's called general linear group of given dimension. General linear group of in real dimension, and you have to specify dimension here. Maybe it is 2, 3, 4, etc. Okay. So when I say if I write 3 here, then it will be a group of linear operators in with real linear operators in 3 dimensions. If I write 2 here, then it will be a group of linear operators in 2 dimensions, and so on. Okay, that depends upon representation. Okay, so for a given group, okay, I will have many such cases. Okay, I will have 2-dimensional operators, 3-dimensional operators, 4-dimensional operators, n-dimensional operators for a given group. Okay, and what is the role of how we decide the dimensionality of the operator? Dimensionality operator is nothing but the dimension of a vector space on which this linear operator acts. See, what is the role of linear operators or linear transformation? They will act on some vector space. Okay, and it will give you another vector space. Okay, so the linear operator, okay, say A, it will act on vector space V, and it will give you another vector space W. Okay, clear? Dimensionality of this vector space decides the dimensionality of the operator. In other words, dimensionality of this vector space decides the dimensionality of the representation. Okay, so we say this is 2-dimensional representation of dot 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 group, or we say this forms 3-dimensional representation of dot 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 group. So when we say that, it means that representation maps a given group to a group of linear operator which will act on 3-dimensional vector space. Clear? Okay. That is, in a nutshell, this is what representation is. Okay. It is a map from a given group to a group of linear operators. And those linear operators will act on certain vector space. Okay. Now, it is a general linear group of general linear operators. It is a group, so there will be an inverse element. Okay, so I should have invertible operation. So that means in general, this dimension of V and dimension of W should match. And without loss of generality, I will say that this is these linear operators will take vector space to itself. Okay, see, this is a group. Okay, for this to be a group, inverse of linear operator should exist. Okay, when inverse of linear operator should exist, if it is a map from same dimension of vector space with some dimension to vector space with same dimension, right? Okay, then and only then that linear operator will be invertible. Okay, so I can have W here with the condition that dimension of V is same as dimension of W. But for a finite dimensional vector spaces, all vector spaces are isomorphic. All finite dimensional vector spaces are isomorphic. Okay. So if you have two vector space of dimension, say dimension of V equal to dimension of W equal to say N, okay, then W and V are isomorphic, basically they are same. Okay. So without loss of generality, I will say that this W is nothing but V. Why we are doing this? Because our wave functions will lie in some general vector space, in particular a Hilbert space. Wave function do not lie in your coordinate space. Wave function set of all wave function form a vector space. That vector space is not your usual R2 or R3, right? It's completely different space. It's certainly not your coordinate space. So the question is, how should I see the action of this group on such a vector space? Okay, that led us to the concept of representation. So the representation allows you to discuss the action of the group element on general vector spaces. Okay. So the rotation in quantum mechanics is nothing but the study of representation of SO3 group. As far as group 3 is concerned, it has nothing to do with quantum mechanics as such. We don't require any concept from quantum mechanics. I can mathematically I can define this without resorting to quantum mechanics or any result in quantum mechanics. In fact, these also, okay, this thing has nothing to do with your classical mechanics or quantum mechanics. This is just purely from your definition of this group, definition of these 3x3 matrices. In physics, we use this to represent rotation. Okay, that is another part, but purely from mathematical perspective, I can have this relation without discussing or without resorting to classical mechanics or quantum mechanics. Okay, so without quantum mechanics, one can have the group representation theory. So don't be under consideration that only in quantum mechanics the representations is useful. No, just from purely mathematical point of view, the representations are there. In fact, this is how the way it is defined. It's not from quantum mechanics to group theory, it's from group theory to quantum mechanics. Okay, so representation basically allows you to check the action of the group on certain vector spaces. If the dimensionality of V is say n, then we say that this R, okay, forms an n-dimensional representation of this group. Okay, fine. I think the definition of representation is introduced to you today or maybe in last lecture, right? In MMP2 course. Am I correct?
Sir, ma'am introduced it today only.
Okay. So you will learn some other more things. Okay. So now what is our job? Our job is to construct representation for rotation. Let me tell you the thing which you know. Okay. You know that if you consider L equal to one state, okay, maybe in say hydrogen atom. Okay. What is the operator for rotation in that case? You know. What is the operator for rotation? What is the matrix, rotation matrix? Or what is the matrix for say LZ? Not rotation matrix, matrix for generator. What is LZ? For L equal to 1, small l equal to 1. What is LZ? Can you tell me quickly? Hmm? LZ acting on 1 m. What you will get? Hmm? What is the action? What should I write here?
MH cut.
M H cross 1 m. How many m values are there?
3.
3. What are those?
1
Plus
0
1
minus
0
1.
minus 1.
1 minus 1 0, right? So you will get this one, then you will get this one, and then you will get right. Now what is the matrix? What is this matrix then?
Diagonal.
But
1
what
0
are the
minus 1.
entries?
1 0 minus 1.
1 0 minus 1,
Minus.
and rest of the entries will be 0, right? Okay, agree? Similarly, you can by using L plus and L minus, you know what are this LX operator and LZ operator, LY operator. Okay, so you know LX, LY, LZ. So basically, you know L, right? You can have the matrix for L. Okay, you can take that matrix and exponentiate it. Okay, and know, and you can from that process you know what is the rotation operator which acts on your states. That rotation operator will be different. That rotation matrix will be obviously different than this. Okay, so here what we are doing, we are considering the representation of rotation on this vector space formed by these states 1m. In this case, we have three-dimensional vector space. But I can consider L equal to 2. Okay, then what will be the case? Then I will have, what is the dimensionality of the state space? Will be what? For L
5.
equal to 2, how many states will be there? 2, 1, 0, minus 1,
5.
minus 2. So 5. Okay. But for L equal to 2 case also, you can construct this 5 cross 5 matrix. Okay, LZ. What will be that? 2, 1, 0, minus 1, minus 2. Okay. Then similarly, you can construct by using L plus and L minus, you can construct 5-dimensional matrix for LX and 5-dimensional matrix for LY. Am I correct? Now, if you consider, if you exponentiate this matrix, okay, if you consider this something, suppose you consider this LZ. Okay, forget about these two for a moment. Okay, you consider this. Okay, this is very legal action, right? E to the power minus I theta LZ. You know how to exponentiate it. Okay, you will get a rotation about Z axis, but this rotation will be rotation operator which will act on this space. This will act on this space and gives me same vector space. Not same vector, same vector space. So this Rz of theta will serve as a linear operator from V to V. So what we are doing? Basically, by doing this, you have constructed a representation for rotation. In this case, it is a 5-dimensional representation, right? Similarly, this representation is three-dimensional representation. Okay. Then you can have six-dimensional representation, seven-dimensional representation, n-dimensional representation in general. Okay. So although rotation is defined in your real three-dimensional space, one can see its representation in any vector space, on any vector space of any dimensionality. In particular, you can ask, can we have two-dimensional representation of rotation group? Okay, and what do you expect two-dimensional representation? Although rotation is in three dimension, and I can have two-dimensional representation. In fact, I can have zero-dimensional representation also. Yes, so here you will see that this will be useful to discuss P. Right? Okay. Your angular momentum quantum number L, small l, okay, is sufficient to specify the representation. Right? You specify L. Suppose you specify L equal L, and that is say 3 or 4. Okay. The moment you give me this value of L, I can construct these matrices, and hence I can construct this representation. Okay. So in this case, in this rotation case, L is sufficient to specify a representation. Or in general, we don't use level L, we use J. So J is the index which specifies the which representation you are talking about. You tell me J, I will tell you which representation I am talking about. And then I can, which representation means, then I can give you all these metrics for that. And it's not that only dimensionality. I can give you full matrix for this, for given J. Okay. So in case of spin, your J equal to half. Okay. And if J equal to half, then you will have two-dimensional representation. But that two-dimensional representation happens to be slightly complicated. Okay, and we will see that in the next class. Okay, so I will continue from this now. Okay, in the next class. Okay, I will. I have defined the representation in very vague manner. Okay, but that is sufficient. Okay, and then I will tell you the problem with J equal to half. If you blindly follow this procedure, okay, then there is a slight problem. What is going to happen is that your usual rotation, see, when I rotate something by 2 pi, you fix the axis, okay, say your axis is fixed along z axis, okay, and you rotate certain object by 2 pi. What do you expect? You get the same state as when theta equal to 0. Am I correct? Okay, so theta equal to 0 and theta equal to 2 pi gives you the same state of that physical object. But that does not happen for a spin. When you rotate this object by 2 pi, you will not get the same object. You will get the negative of that. In fact, when you rotate by 4 pi, you will get that object. You will get the same object. Okay. Usually, under rotation by 2 pi about some fixed axis, you get 2 pi and theta equal to 2 pi and theta equal to 0 are the same same elements in that rotation group. Okay, but for spin, it's the story is slightly different. You will get, if theta equal to 0, you have the identity matrix, no rotation. Then for theta equal to 2 pi, you will get minus of that identity. Okay. Then theta equal to 4 pi, you will again get the identity. Okay. This happens because this spin actually is not okay. Okay, let me tell you, let me go in this way. Okay, so the group of transformation to discuss spin is not exactly SO3. It is SU2 basically. Okay, there's no harm in considering SO3, but then you will get these sorts of problems. In other words, this the representation which I was talking about. Okay, this is not 1-to-1. It is 2-to-1 map. It's not just 1-to-1 map. It is 2-to-1 map. Okay, so that is the only problem. So apart from this 2-to-1 nature, okay, everything whatever we discuss for SO3 holds for SU2, but that creates difference. Okay, this part create difference. Okay. For a map to be isomorphic with some another map, okay, okay, for a group to be isomorphic with some another group, okay, we should have 1-to-1 mapping. Okay. Otherwise, we will call it homeomorphic. You must have heard these words in your MMP1 class. Okay. I have here 2-to-1 homeomorphism between SO3 and SU2. If you give me 2-to-1 homeomorphism between SU2 and SO3, you give me two elements of SU2, okay, and I will tell you that certain two elements maps to same element in SO3. So you cannot identify these two elements. So as far as SU2 is concerned, these 2 points are different. But as far as SO3 is concerned, it is same point. Okay. So we'll discuss that later on. Okay. So I will just briefly mention what is the problem. I will not go into detail, but I will briefly mention about the problem. Okay. So I will give, we are interested in this spin representations of rotation group. And now I can use this spin representation to classify the Lorentz group itself. Why? Because I know that Lorentz group can be written as a direct product of SO3 cross SO3. So what I will do, okay, I will take one J from one SO2, okay, say this one J from one SO3, and I will take another J from another SO3. And I will form these representations now. Okay, so I will have J equal to 0, J prime equal to say half. Okay, then I will have J equal to half, J prime equal to 0. So I have 0, half, then I have half, 0, then I can have half, half, right? In general, I have J prime. And if I know how to get the rotation operator in these representations, then I know how to get rotation operator in any representation. Hmm? Okay, and your Dirac spinner happens to be in this case, in this part. Okay, we'll see that. So I will stop here. I do not expect any question because it's slightly heavy. So you think over this, and in next class we will go into the spinal representations of rotation group, and then we will connect it to Lorentz group. And once I have that, then at that moment I will know how the Lorentz transformation acts on the wave function. Okay. But still, if you have any question, you can always ask. This part is not required as such. If you see the textbook, okay, they will give you just transformation property. Okay? But one has to understand how this is coming, and this will be useful in the field theory. Field theory, this is required. As far as your relativistic quantum mechanics is concerned, one can avoid this. One can directly start by assuming that this is how your spinor transform, this is how your direct four component object transform. But one has to understand what does it mean. So again, I advise you to read chapter 3 of Sakurai. The representation for rotations are given there, and we will require that. If you have not done, please go through it. Okay, any question? If not, then we'll. Yes.
Sir, for spins, you said